Euclidean Geometry, Grade 12 Mathematics, Paper 2. Right, we're discussing Euclidean Geometry revision. Let's have a look at this question and how to approach questions like this. These kind of questions, they normally involve all trigonometric ideas that you have learned from circle geometry to proportionality, similarity, midpoint theorem, parallel lines and properties of triangles and quadrilaterals and so on. So basically, you have to throw in every geometry spanner you know here to be able to answer a question like this. So let's have a look at how we can answer. You probably can pause and answer it yourself. Then when you're done, you can go ahead and go through the answers to see if you got them right or not. When answering questions like this one, I normally advise that don't start by worrying yourself about what you need to calculate, what you need to prove, and the things you need to do. That is the least of your worries. The first thing to do is to ask this question. What are the theorems that are being tested by this question? How do I identify them? So I must look for keywords that can help me or that can connect me to the circle theorems or to geometry theorems that I know. The first word that you cannot miss is the center of the circle. M is the center of the circle. Now that word alone has a lot to do in geometry. The center of the circle reminds us. It tells us about the angle at center is twice the angle at circumference. It might be there in the diagram. The center also tells us about the radii. If the radius is connected, now like in this case now, if you look at my diagram, I have line AM. The line AM versus line MB and line MD. Those three lines are all equal to each other. They are representing the same measurement, which is the radius. Now in triangle AMB, triangle AMB is now an isosceles. We have discovered that it's an isosceles triangle. So angle A and angle D2 are equal to each other. They are angles opposite equal sides. Then D3 is equal to angle D2 because triangle MBD is also an isosceles triangle. Just that example, this has come from one word, the center of the circle. So I must look for keywords, and one keyword is the center. It is connected to so many theorems or so many ideas that we can use to answer the question. The next one is diameter. We know about the diameter. The diameter subtends an angle of 90 degrees. So in our diagram, we can see that at point D, D2 plus D3 is equal to 90 degrees because the diameter subtends a 90-degree angle. What else do we have? We have CDE, which is a tangent. Now, the tangent tells us about the tan-chord theorem. Very critical, and I must know in my thoughts how to identify angles that are equal using the tan-chord theorem. So the tan-chord theorem, we have one triangle. You look for a triangle, and there is one line touching the one part of the one vertex of the triangle. That is the tan-chord theorem. So you look for a line, and the line must be touching one vertex of the triangle. Then in the circle, the 3 points of the triangle are touching the circumference of the circle. That is tan-chord theorem. So how do I know that there is tan-chord theorem in the diagram? They won't say, oh, here is the tan-chord theorem. No, the question will tell you one item. Line CDE is a tangent. Once they tell me that line CED is a tangent, then on my own, I will now know what it means, and I'll also know which angles are equal in my diagram. So my question starts by making sure that I have an analysis of the question, and my analysis of the question seeks to find out what information is available for me in the diagram. Once I get that, then I'm good to go. So if I get this, and if I draw a line here, now if this line is my tangent, then I have a chord. The angle between the chord and the tangent will be this one. Then it must equal to the angle in the alternative segment. So in this diagram, we have got the center, the diameter, we have got the CDE, which is a tangent. When you are done looking at all these ideas, you still have to ask yourself, are there any other relationships given? So we can sometimes get equal angles or lines that are equal. In this case, we have got MB, which is equal to 2 times BC given. So we have all the information, and I don't think we have missed anything. This line here, this is another relationship that is important. We have everything together, and now what we need to do is to connect them to produce the answers that are required. We are told that the value of angle D4 is equal to x. So using the tan chord theorem, we can find more angles equal to x. So that is angle A is equal to x. Angle D2 is equal to x because A and D2 are the same. We can also find that the angle M1 is equal to 2x. That is an exterior angle of a triangle equal to the sum of opposite interior angles. Then the value of angle D3 will is equal to 90 minus x, because the D2 plus D3 is equal to 90. Then we can calculate angle B2 using angles in the triangle add up to 180. We can also find B1. If we subtract 180 minus B2, it will give us the value of angle B1. So once you put your information together, you are now able to go ahead and answer the questions. It will become very much easier to find the angles that are required, or to do the proofs that are required once you do a clear and thorough study of the question that you are answering. All right, this is my question. So from here, I can carry on. The last part given there, MB is equal to 2 times BC. It can help us create relationships. If BC is equal to R or X, then it means we can find MB as a 2 times R. That is Euclidean geometry for us. Very nice. Answering question 2.1. From the information that we have gathered by analyzing the diagram, we notice that at point M, M is the center. We have a 90-degree angle there. Then we have line AM, which is equal to line MD. That makes triangle MAD an isosceles triangle. MB is equal to MD. That makes triangle MBD an isosceles triangle. Then we have angle D4, which is given. So if we look at the position of angle D4, it is an angle between a chord. The chord is BD and the tangent is DC. This is an angle between a tangent and a chord. So this angle D4 must equal to angle X by tan chord theorem. But angle A is also equal to angle D2. Angle A is equal to D2 because of angles opposite equal sides from isosceles triangle AMD. So we have already the answer for question 1. A is equal to X by tan chord theorem, and D2 is equal to X, angles opposite equal sides. That is our answer for 2.1. 2.2, we want to show that SM is a tangent to a circle passing through MED. The circle itself is not there, so we can put the circle ourselves draw a circle or just have it in your mind. If we have our circle passing through point MED as indicated, then if you look at the angle M1, we can notice that the value of the position of angle M1 is between line CM, which is a tangent, and line MD, which is a chord. So therefore, it must equal the value of angle E. If we show that M1 is equal to angle E, then we can conclude that CM is a tangent using the tan chord theorem. Now, with everything that we have done so far, angle M1 and M2 combined, they are equal to 90 degrees using angles in a triangle add up to 180. Since M3 is equal to 90, it follows that M2 plus M1 combined also equal to 90, which means M2 must be 90 minus 2x. This is the value of M2. And a reminder, the value of M1, which is equal to 2x, we got this one from exterior angle. An exterior angle of a triangle is equal to the sum of opposite interior angles. So adding angle A and D2 gave us M1, which is equal to 2x. Now, we can calculate the value of angle C using triangle ADC. Interior angles in a triangle add up to 180. Therefore, that allows us to calculate the value of angle C by subtracting from 180 degrees. So that will give us 90 minus 2x. Then if we shift our attention to triangle MEC, we can calculate the value of angle E using angles in a triangle add up to 180 degrees. So we know that the angle at point M, M1 plus M2 combined, they equal to 90 degrees. Then we have calculated the value of angle C, which is 90 minus 2x. We can now find the value of angle E using angles in a triangle add up to 180. So if you work out that answer, we get E is equal to 2x. Now the value of angle E is equal to 2x, and the value of angle M1 is also equal to 2x. Therefore, line CM is a tangent to the circle at point M. This is coming from the converse of the tan chord theorem. That answers question 2.2. So 2.1 and 2.2 are done. Once you put information together, it becomes very much easy to see the relationships that you must connect to produce the answers that are required by the question. Right, question 2.3 and 2.4 prove that FMBD is a cyclic quadrilateral. That is a straightforward calculation because if you look at the shape that they are mentioned, this is my quadrilateral. We have angle M3 here, which is 90. Then angle D2 plus D3 combined, this angle here, we also have got a 90-degree angle because it is angle in a semicircle. Remember, point M is the center of the circle. Therefore, line AB is a diameter which subtends angle D, 90 degrees angle in a semicircle. We have a theorem that says an exterior angle of a cyclic quadrilateral is equal to opposite interior angle. If we are to put a circle around here, we can see that M3 is an exterior angle and D2 plus D3 combined, and that is the interior angle. Therefore, FMBD is a cyclic quadrilateral. That is my answer for question number 2.3. Now, the reason for the last one is the converse of the exterior angle of a cyclic quadrilateral is equal to opposite interior angle. Number 2.4, you can figure that out on your own actually. In triangle MDC, Now in triangle MDC, we have MB is equal to MD. We have already figured this out right in the beginning. MB is the radius and MD is also the radius. So yeah, MB, MD, the radii, we already established that one. And we are also making use of this relationship here. MB is equal to 2 times BC. Then we can do substitution. The value from M to C is equal to 3 times BC. So if you were to make this one x, then this one will be 2x. And that means MC squared is equal to MD squared plus DC squared. Normally, this kind of last questions, they are heavily dependent on the relationships that have already been established. So once you do the first questions right, the next ones connect with each other very nicely to produce the answers that you may need. That is my geometry question answered for 2023 for a number of marks. It's very much necessary to revise and go through these kind of questions because that's what we expect in grade 12 Euclidean Geometry. The last two questions, number 2.5 and 2.6, prove that DBC is similar triangle DFM. We must have all the information that we have calculated at hand. This angle, we know it's equal to 2x. That one there is x, this one is x, and this one is 90 minus 2x. We also calculated angle C, and we got 90 minus 2x. We can find F2 using angles in a triangle add up to 180. We can also find F1 using angles in a triangle add up to 180. Now, we want to compare angle DBC. Angle D is D4 and angle B is B1. Then in angle triangle DFM, D is D2 and F is F2, DFM, and M is M2. So similarity, you look at the first letter and the first letter. Angle D4 in comparison to angle D2, are they equal or not? And if you look at our diagram, you'll see that D4 and D2 are both equal to x. Then we look at angle B. We need B1. B1 in comparison to angle F2. Are they equal or not? Then finally, we look at angle C compared to angle M2. C and M2 are equal. We can see that M2 is 90 minus 2x and angle C is 90 minus 2x. That completes number 2.5. Because once we get two pairs of angles that are equal, it completes your answer immediately. So M2 is 90 minus 4, D4 and D2 are equal to each other. This one has already been proved. Then M2 is equal to 90 minus 2x. C is also 90 minus 2x. Therefore, angle M2 is equal to angle C. Then the third angle, we can say they are equal because angles in a triangle add up to 180. and therefore the triangle DBC and DFM are equal to each other. Angle, angle, angle. That's about it. Once your information is there, you are set to go. I'll leave number 2.6 for you to do, but in general, we know that when two triangles are similar to each other, we divide the sides of the two triangles. The first two letters over the first two letters, the second to the third over the second to the third. Then the outside divided by the outside. That is the concept of similar triangles. The sides of the triangles are in the same proportion. So dm over fm, in our case, we want to find dm over fm. So if you look at the way the lettering is ordered in dm is in this one here. That's from D to M is dm divided by fm. I can also do the same thing on this side, dc divided by bc. The way you order the letters on the left and on the right must be the same to create the fractions you need. So from there, we do substitution and calculate our answer as is required. That is our Euclidean geometry. These sections, they are normally blank in paper 2. So we're hoping that when you write your examinations, it's not going to be blank for you. You must be able to know what to do. It comes with practice, it comes with a lot of studying, and it comes with a mind that is determined to get things done.